What happens if you enter a black hole? Well, what happens if you fall into a black hole? This question has echoed in our minds for decades. Born from science fiction and the frontiers of physics, it speaks to our fascination with the ultimate unknowns of the cosmos. Imagine a small spacecraft drifting through silent, cold, interstellar space. You, an explorer, light years from home, in the distance, something impossible. Not a star, a patch of perfect blackness, a hole punched in the fabric of the universe, surrounded by distorted starlight and warped galaxies. It pulls you in with gravity and with irresistible curiosity. Not a movie scene, a real place, a black hole, immense gravity, a region of space-time where gravity is so strong nothing, not even light, can escape. To know what happens, we must embark on a journey that will test the limits of our imagination and the laws of physics. Set aside everyday intuition. Prepare to enter a realm where space is not empty and time is not constant. To understand the fall, we must first understand the object itself. What is a black hole? It begins with the death of a truly massive star. Stars are immense nuclear furnaces. They spend billions of years fusing lighter elements into heavier ones in their cores. This releases tremendous energy. That outward push balances gravity, but not forever. Eventually the fuel runs out. Gravity wins. The star collapses under its own immense weight. For very massive stars, the collapse is catastrophic. The core implodes, crushing matter into an unbelievably small dense state, squeezed into a point of zero volume and infinite density. This point is called a singularity, a place where physics breaks down. The laws of space and time cease to apply. The singularity is the heart of the black hole, the source of its gravity. It warps space-time dramatically. Imagine space-time as a flat, flexible sheet. A planet like Earth, a small dimple, a star, like the sun, a deeper dimple, a black hole, a bottomless well, a puncture in the fabric of reality. This curvature is what we feel as gravity. It dictates how objects move. Near a black hole, all paths lead inward toward the singularity. Surrounding it is the event horizon, an invisible boundary, not a physical surface. You could pass through without feeling a thing, but it is the point of no return. Past it, escape velocity exceeds the speed of light. Nothing faster than light, nothing gets back out. The ultimate one-way membrane. Information, light, matter. Anything that falls in is trapped forever, sealing the black hole's secrets from the outside world. Our journey starts in safe, normal space. Here, the black hole is a predictable gravitational influence. Closer in, the universe changes, rules bend and break. It's not just a fall into darkness, it's a descent into a new reality science still struggles to understand. The question is simple. The answer is anything but. What happens if you fall into a black hole? The universe holds the answer, waiting for us to listen to its story. As you approach a black hole, even before you reach the event horizon, the universe begins to look very strange. The immense gravity acts as a powerful cosmic lens. It bends the path of light rays that pass near it, distorting your view of the stars behind. You would see multiple images of the same star, warped, smeared, duplicated, a swirling vortex of celestial light. The black hole remains a perfect circle of blackness. Its shadow, larger than the event horizon, is the silhouette of the abyss, ringed by photons looping around before escaping. Time itself behaves differently. According to general relativity, gravity warps time. The stronger the gravity, the slower time flows. For you, your clock ticks normally, but from far away, your clock seems to slow. Your movements turn sluggish, your light redshifts and dims. To them, you freeze just outside the horizon, never quite crossing. For you, the journey continues. You pass through the event horizon in a finite, very short time. Let us place ourselves back in that lonely spacecraft. The initial approach toward a supermassive black hole, 1 millions of times the mass of our sun, might feel surprisingly gentle. From a distance, its gravity is like any massive object. You can orbit it safely, just as planets orbit a star. The danger is not immediate, but as you choose a path that crosses the horizon, its true nature reveals itself. Not with a jolt, but with the creeping influence of tidal forces. We know tides from the moon and Earth. a slight difference in pull across a body. Near a black hole, amplify that difference beyond imagining. As you fall, the pull on your feet is stronger than on your head. At first, it's imperceptible, a subtle tension. Closer in, it grows exponentially. Every atom feels a slightly different tug. You, your spacecraft, your belongings, all are drawn out into long, thin strands. Astrophysicists have a name for this. It is called spaghettification, being stretched into the shape of a noodle, not only stretched, but squeezed from the sides, funneled down a ferocious gradient. For smaller black holes, this ends outside the horizon. Your journey becomes a stream of atoms. But for a supermassive black hole, you might cross the horizon intact. The reprieve is temporary. Inside, the stretching begins in earnest. The event horizon is a place of profound paradoxes. For the distant observer, you are frozen in time, fading into nothingness. For you, the journey continues. Approaching the invisible line, the sky compresses. The external universe becomes a shrinking circular window. Its light blue shifted, energized by your fall. The moment you cross is unremarkable. No wall, no signpost, no cosmic alarm bell. You slip from a region where escape is possible to one where it is not. Inside, reality alters. Space and time swap roles in a way hard to visualize. All spatial directions now point toward the singularity. There is no turning back. Fire your rockets, try to turn or go sideways. It's as futile as traveling back to yesterday. The flow of space-time carries you forward. The darkness is absolute. No light from outside can reach you. You are cut off from everything you have ever known, alone in a collapsing pocket of space-time. Your view of the singularity is uncertain. Relativity and quantum mechanics give conflicting predictions for what happens at this extreme point. Some models suggest a point of infinite density. Others propose vibrating strings, a fuzzball, or a quantum foam where space and time dissolve. What you would see is a mystery, perhaps a wall of fire, perhaps simply the end of existence. To truly understand the center, we need a theory that unites relativity with quantum mechanics. Dantaduan Sino, Lantibur Dam, Kasaninan, Ansabur Bam. Gravity. Ideas like wormholes inspire us, but face daunting hurdles. String theory suggests black holes may be fuzzballs, with information stored on their surface rather than destroyed. As you complete your journey, you fall into the biggest gap in our scientific knowledge. A black hole is nature's ultimate laboratory, its results hidden from us. What if we one day find out?